Dear students, in today's lecture we are going to study dielectrics and electric polarization. Then first of all we will study the meaning of dielectric. So dielectrics are nothing but insulators, or these are non-conducting materials. Again, these dielectricals have no free electrons, and dielectric transmits electric effect without conducting. Also, this dielectric stores large amount of electrical energy. And these dielectrics are of two types. One is called as Polar Dielectric and second type is non-polar dielectrics. Then, what do we mean by polar dielectrics? So the substance in which the center of mass of positive charge, that is proton, and center of mass of negative charge, that is electron, do not coincide. That means the center of mass of both positive charge and negative charge are separated. And this is because of asymmetric molecules. And the examples of these polar dielectrics are H2O, HCl, NH3, alcohol, etc. So polar dielectrics are nothing but the substances in which the center of mass of positively charged and center of mass of negative charge do not coincide. They are separated because of their asymmetric in nature. And examples we have seen, which is H2O, HCl, NH3, alcohol, etc. So for example, if we take H2O, so this is H, this is another molecule of H, this is the molecule of O, then this is positive, this is negative. Then the center of this H is here and the center of mass of oxygen is here. Therefore, the electric dipole moment is directed from negative to positive. That means, in case of polar dielectrics, there are electric dipole moments in the presence of electric field as well as in the absence of electric field. But when electric field is absent, then in case of polar dielectric, the electric dipole moments are randomly oriented. This is minus plus, minus plus. These are the electric dipoles. And these electric dipoles are randomly oriented if no electric field is applied to the polar dielectrics or molecules of polar dielectric. If we apply electric field to this polar dielectric, then all the electric dipoles have net electric dipole moment in the presence of electric field. So here E is not equal to 0, that means E is applied. So in case of polar dielectric, in the absence of electric field, the substance possesses net electric dipole moment, but it is equal to 0 because the electric dipole moments are randomly oriented. But when electric field is applied, then the polar dielectric possesses net electric dipole moment and they behave like tiny electric dipoles. The second type of dielectric is non-polar dielectrics. And in case of non-polar dielectrics, the examples of these non-polar dielectrics are H2, N2, CO2, methane, benzene, etc. So from the examples of non-polar dielectric substances, we observe that these substances are symmetric in nature. So H2, N2, O2, CO2 have symmetric in nature or their shape is symmetric, and hence the substances in which the center of mass of positive charge and the center of mass of negative charge coincides, that means are not separated due to symmetric in nature or symmetric in shape are called as non-polar dielectrics. And in case of non-polar dielectrics, in a normal state, the non-polar dielectric or substances does not possesses any electric dipole moment. That means if electric field is equal to 0 is applied to non-polar dielectric substance, then they do not possess any electric dipole moment. That means electric dipole moment is absent in normal state in the absence of electric field. But for this non-polar dielectrics, if electric field is applied is not equal to 0, then it possesses partially electric dipole moment, or it have partial electric dipole moment. And when it is placed in electric field, they also have tiny electric dipole moments. So, if we summarize this polar dielectric and non-polar dielectric, then the first point is, so polar dielectric and non-polar dielectric substances. So first point is center of mass of positive charge and center of mass of negative charge do not coincide. And in case of non-polar dielectric, center of mass of positive charge and center of mass of negative charge coincide. And the substances or polar dielectrics are asymmetric in shape, and these non-polar dielectrics are symmetric in shape. Third one, we have seen the examples of polar dielectrics, which is H2O, HCl, alcohol, NH3, etc. And the examples of non-polar we have seen H2, O2, N2, methane, benzene, CO2, etc. And fourth point we have observed, these polar dielectrics have electric dipoles in the absence of electric field also, but they are randomly oriented, and therefore net electric dipole moment is equal to 0. But when electric field is applied, then we get inside the polar dielectric net electric dipole moment. In case of non-polar dielectric, when E is equal to 0, they does not possesses electric dipole moment, but in presence of applied electric field, they have partially electric dipole moments. That means, from today's discussion about the polar dielectrics and non-polar dielectrics, we conclude that both these polar dielectrics and non-polar dielectrics, when placed in external electric field, the molecules of these dielectrics induces electric dipole, and when the induced dipole are present, when electric field is applied due to displacement of positive charge and negative charge, or when electric field is applied due to stretching of the molecules or orientation of the molecules, dielectric medium possesses electric dipole moment. So we will discuss the next term, which is called as electric polarization. So electric polarization can be explained by if the electric field is developed between the two plates of due to uniform distribution of the charge, then let us suppose that plus Q be the charge on one plate and minus Q be the charge on the second plate, and these two plates are separated by a small distance d. Due to the equal and opposite charges on these two plates, electric field is developed between these two plates, and this electric field is given by E0. That means the electric field between the two plates in the absence of dielectric. Dielectric may be polar dielectric or it may be non-polar dielectric. That means between two plates a medium present which is air, and therefore this electric intensity between the two plates is directed from positive plate to negative plate. So here E0 is the electric field between plates with air. Now, if we insert a dielectric material which is polar or which may be non-polar dielectric is inserted or introduced between these two plates, due to which electric field is produced, that is E0. As the dielectric is introduced, then due to stretching and reorientation of the molecules, or the positive charge and negative charges inside this dielectric gets displaced. So due to stretching and reorientation or displacement of the negative and positive charges inside this dielectric, electric dipoles are produced. Suppose the electric dipoles produced inside this dielectrics are so when electric field is applied to the dielectric, we will get net electric dipole moment inside the dielectric, and the resultant electric dipole moment, which is P, and this P is directed from positive plate to negative plate. That means net electric dipole moment is in the direction of applied electric field, that is E0. Now, as the dielectric possesses net electric dipole moment, then the charges towards the left of the positive plate inside the dielectric and the charges towards right of the negative plate, they remains as it is, and the remaining charges which are present inside this, so at the boundary of this dielectric, net negative charge is present, and this net negative charge, that is polarized electric charge, and the net positive charge is present on the right side of dielectric, which is near to the plate minus Q. Then due to that, net polarized charge towards right is minus QP. That means plus QP and minus QP are induced electric charges or polarized electric charges. So QP and minus QP are polarized electric charges, also called as induced electric charges. That means electric polarization takes place inside the dielectric, and when electric polarization takes place, then near the positive plate, net positive polarized charges are remains, and on the right of the dielectric, near the negative plate, net positive charges are present. So on the left side there are minus QP charges, and on the right side of dielectric there are plus QP charges. And as all these charges which are near to the plate, positive and negative on the surface of the dielectric, they are minus QP and plus QP, and due to these charges an electric field is produced, and the direction of this electric field is from plus QP charge to minus QP charge. That means polarized positive charge to polarized negative charge, and it is denoted by EP. So the direction of electric field due to charges on the dielectric is EP, and it is directed in opposite direction of applied electric field. So as E0 is directed here from left to right, and due to induced charges the electric field is developed, which is EP, and is directed from right to left. And because of these two electric fields, first one is E0, which is the original electric field in the absence of dielectric, and another electric field which is EP, which is produced due to polarized electric charges or induced electric charges, and these electric fields are directed opposite to each other, and hence there is a net electric field, that is E net, between the dielectric is given by E net is equal to EP minus E0, and also this E net is also called as E reduced. So reduced in electric field intensity, when the dielectric is introduced, it is E reduced or E net, which is equal to electric field due to polarized charges minus electric field in the absence of dielectric. So E reduced is equal to EP minus E0, and this formula we will use in our next article. Now our aim is to define the electric polarization. So to define electric polarization, we have studied the electric field in the absence of electric field. When dielectric is placed, then induced charges are produced on dielectric. Then electric field due to this induced charges is opposite to the direction of applied electric field, and hence net electric field is EP minus E0, or there is a reduction of electric field. Now electric polarization is a vector quantity, and this electric polarization can be defined as, so electric polarization P is equal to net or induced electric dipole moment per unit volume. So due to polarization, that means when the dielectric is present in the electric field, charges are induced and electric dipole moments are produced inside the dielectric. So electric polarization is net or induced electric dipole moment per unit volume, and from this the SI unit of electric polarization P is given by the SI unit of electric dipole moment is coulomb into meter divided by unit of volume is meter cube, and therefore we get the SI unit of electric polarization is coulomb per meter square. So this coulomb per meter square is the SI unit of electric polarization. And this electric polarization can also be defined as electric polarization is equal to sigma P. That means charge density of polarization charges, which is sigma P, or this can be written as Q divided by QP divided by A, polarized charge per unit area. So electric polarization can be defined in three manners. One is net or induced electric dipole moment per unit volume, or it can be defined as the polarization charge or induced electric charge per unit area. And again, from this formula, Q by A is nothing but surface charge density. So in the similar manner we define electric polarization is nothing but charge density of polarized charges or charge density due to polarized charge. And from all this formula, the SI unit is come out to be coulomb per meter square. So electric polarization is nothing but net electric dipole moment per unit volume, or it is nothing but polarized electric charges per unit area, and it is also equal to charge density of polarized charges. And this electric polarization P is directly proportional to the electric field applied. So electric polarization is directly proportional to the electric field applied, and therefore we write, so electric polarization P, which is equal to epsilon 0 into chi E into E, where this epsilon 0 into chi E is the proportionality constant, and this proportionality constant epsilon 0 into chi E is similar to 1 upon 4 pi epsilon 0, which has taken constant in Coulomb's law in electrostatics. So electric polarization directly proportional to E, if proportionality constant is replaced by the quantity which is epsilon 0 chi E into capital E, then from this expression we write chi E is equal to P divided by epsilon 0 into capital E. And in this equation, this chi E is called as electric susceptibility. So chi E is electric susceptibility. On right hand side, P is called as electric polarization, epsilon 0 is called as permittivity of free space or vacuum, and E is the intensity of electric field applied. So electric susceptibility is equal to P divided by epsilon 0 into E. If we substitute the SI units of electric polarization, SI unit of epsilon 0, SI unit of electric intensity, that means the P electric polarization has unit coulomb per meter square, epsilon 0 has unit coulomb square per Newton meter square, then E has unit Newton per coulomb. If all these units are substituted in this formula, then SI unit of electric susceptibility, so chi is SI unit is nothing. That means chi E is a unitless and dimensionless quantity. Chi E is a pure number. So electrical susceptibility is a pure number which does not have any unit and dimensions.